And as I said, you have the A and B here, and then you have a quantized value. Because so far we were using the U of k, right? Assuming that there is no quantization. But with the network, you also get the quantization effect. Now, the professor asked me earlier, what is lossless? Because, lossy and lossless we use in electrical engineering. The same idea. Here, lossless means information loss. So whenever you have a network, you have packet loss. So you're losing that information, therefore lossless means you don't have any packet drops or you don't have any delays. Remember that. Got it? So the same idea, they also use lossless. The same terminology. Okay? So you see the control input here, you're using the quantized state value rather than x of k. So that's the difference between what happens, unfortunately. So there were questions about what is quantization. Now, remember, and how is it different from when we take a variable like a Euler's method, you convert a continuous variable to discrete. Now, mathematically, you won't see any quantization error. Okay? But there exists always a quantization error that comes from the hardware. Remember that. That's the difference. Like computers have finite word length, right? There's a round of errors. But when we do mathematically, you ignore all those. But in practice, when you're implementing it, you will see those. A lot of times we ignore that, and that's what I'm going to show you. You really can't ignore those. See? Alright. So here is the quantized stuff. So you can see that the original value, and here is the quantized value on the y-axis. Now you see the dotted line, a straight line. That is the ideal quantizer called the mathematics. So basically, that's a linear line which says that based on the current value, you get a quantized value. So there's no loss. You understand that in the linear line? That's what mathematics does. But in hardware, you see that there's a step function. That's where the hardware does it. Remember that? Okay? Now guys, you don't have to copy these slides, right? You will be given those slides. If you register for the class, you will get a copy of the slides, right? So you want to pay attention to what I teach rather than busy on taking. You can take notes if something is not there, okay? So now you see this here, the step function is the quantized value. And that quantized value has an error. That's number one. Number two, the quantizers have a saturation. You see here, m is the maximum value minus m is the minimum value. Mathematics says there is no saturation. That's in the idea of quantizer. But there's always going to be a saturation based on number of bits. If you only have 4 bits, you can only express so much value. Anything above that, you only get value of m, not anything. You see what I'm saying? So this is where that saturation plays a bigger role in it. Okay? So the drawbacks are, even though the quantized error is bounded, the bound can be large. We also have saturation. Anything above this m gets truncated to m. And these can cause serious problems to control. You understand that? Because you're asking, let's say 5 Newton meter, because of quantization, you may be getting only 3 or 4. So there is a problem. You see what I'm saying? There is a problem. Now we also will talk about actuator saturation later in the nonlinear part of it. Actuators also have a saturation. Now if you have run a motor, let's say they'll tell you the motor runs at 1500 RPM, right? But even if you increase the voltage, it won't increase the speed. It stays there at 1500. So actuators also have an saturation effect. So we'll see that in the next part of this presentation, lecture 6, where there is an actuator saturation. Okay? So there are 2 things you will see in the quantizer. One is saturation. The saturation is you think it's a value above m, but m is the limit minus m of m. There's also bounded quantization error within m, and that's expressed mathematically is if norm of z is less than or equal to m, then the error is given by that. If z is greater than m, then the error is given by that. And actually, it is, these are standard equations. You can play with them, you know? Okay? So now, we are going to go into dynamic quantizer because static quantizers have problems, and I'm going to show you the simulation. The MATLAB code you can simulate it, okay? So what is a dynamic quantizer? So to overcome these problems, if something is outside that limit, I'm going to use what we call zoom parameter. It's a scaling parameter. That scaling parameter in the dynamic quantizer will push the system outside the range to inside the range. You see? And that helps so that you don't have the bounded errors. So that's one of the benefits of the dynamic quantizer. And the dynamic quantizer equation is given by this. So you have two quantizers, one in the state, one for the control. So you see that mu x comma k q of, that's the quantizer divided by this. So we adjust that mu so that mu x comma k, that's for the state, mu u comma k, those are called zoom parameter. And the purpose of the zoom parameter is to eliminate saturation, shrink the quantization error over time. Okay, so normally in a regular quantizers, the more the number of bits, the quantizer error goes to 0. You see what I'm saying? So, but ideally, there's always the AD to DA converters or even the network as a finite number of bits. Okay, so this is why, if you remember, they say that this company came up with 64-bit processor or 32-bit processor. So those bits essentially make a difference for us. Okay? So the zoom parameter helps to eliminate the saturation, and it also helps to shrink the quantization error over time. Got it? So, and the way you compute is the quantization error, which is given by the E, x comma k is given by the quantized value minus the actual state value, and that is expressed in terms of mu and then the step size delta, and that is basically bounded by E m of x, the upper limit. And this is the control. This is also bounded by m, and we are defining mu x comma k is the norm of x of k divided by that beta and gamma. Essentially, you can crank it up. If you crank it up, it pushes any values outside the range, it brings it inside, and it makes it nicely for you, like a nonlinear. So this way, the dynamic quantizer by Liberzon, this guy who developed that Liberzon, this quantizer eliminates the problems that you see from traditional quantizers. Do you understand that? Eliminates the problems that you see with traditional quantizers. Traditional quantizers are called uniform quantizers, and all uniform quantizers have saturation problems, which is dictated by the board length, which is the processor or whatever you use in your ATTDG. Okay? So there are issues with it. So now we want to use the optimal control policy with quantization. So we're going to start with linear systems. So what will happen when there is a quantization effect? And I'm going to show you in the derivation. I'm going to skip the derivation, but I'm going to show you. So we use the same idea I showed you, like a linear system. V of x of k, this is the finite horizon. X of k transpose S of k, where S is obtained from the Riccati equation. You see there is an expected value because we are assuming that, you can assume it's lossless, you can also add that. You have a network, you can also add it. Doesn't matter. Okay? Now look at that, Hamiltonian. So you define the Hamiltonian. This Hamiltonian is nothing but the temporal difference error. The same temporal difference error is equal to 0. So the same thing. If the Hamiltonian is 0, that means optimality. Okay? Or the temporal difference error goes to 0 means that's basically the condition for optimality. Don't forget that. Okay? But in real life, you will have some error, and the goal is to drive that error to 0 by selecting that update laws and so forth. Okay? So now, and you use that Hamiltonian and you come up with that partial H over partial. Now look at that. Here I'm using the quantized value Q of K here. Okay? So now what happens is if you take partial H over partial U QK, you end up in two terms. Now look at that. The first term is same as the Riccati equation. The control. Look at the second term. The second term has errors in the quantization errors in the state as well as the quantization error in the U. You see? So the derivation is identical to what we showed before, but now what you do is you actually write wherever there is x of k, you write it as E of error, quantization error plus that quantized value. So in other words, remember, so what I'm doing is I'm defining, which doesn't show here, so I'm defining the quantized error, let's say E x comma k is equal to some x qk or xk minus x of qk. So this is the quantized value and this is the real value. So wherever I have the state or the control input, the same thing. Here I have a control input. So I have u of k minus of u of q comma k, something like that. So what I'm doing is wherever I have a qk, I have to replace that by u comma k plus u of q comma k. So I'm replacing that. Because of that term, the error term coming in, you get an additional term here. That additional term is because of the quantization error. So far, we didn't see that error because we assume that there is no quantization. You see what I'm trying to say? So you follow the same derivation, you get the same equation, and you get an extra term. Now if you are using traditional quantizers, like I showed you, this term will not be zero. You see what I'm trying to say? That term will not be zero. So you get some error in your expected value of the quantized control input. Okay? You get an error. But if you use the dynamic quantizer, that error becomes zero. That's the difference why we use the dynamic quantizer. Now, does the current hardware uses it? I don't know. But this is done in 2000. Maybe they are using a dynamic quantizer. So that is the contribution of Leverzahn in one of his papers.
But in the current scenario with 64, like, everyone have 64. But
the error, you still will have an error, but it's proportional to the number of bits.
Quite small. I do not understand that quantization.
It is small, but what people have shown is it can still cause instability.
That type of situation, that type of problem.
It is currently there. People don't, that's what we were discussing with some students, people don't realize that in some cases you don't, and that depends on how fast is your system. That again comes in that perspective. If you, for electrical systems, the time constant is usually very small, like motors and stuff. Yeah, but whereas you take, look at the solid state, let's say for power electronics, they switch very fast. Sure. But you understand the difference, right? It's real. It's real. In communication systems, power electronics, because they use those wide gap semiconductors and they have a very fast switching. Go ahead.
Another thing, you are I have not seen, but dynamic controller, what is new something and multiply?
It is multiplied and they divide it and then they adjust the division. So they crank up, that's called zoom parameter. So what happens is if you have a value outside the saturation range, by cranking up the zoom parameter, scaling, you are trying to scale it and you are pushing it inside the saturation of the quantities.
But overall you will change.
You will change. You will change, but it still works and I'll show you. It still works.
It is better than the saturation.
That is correct.
That has to be put in
That is
correct.
Okay, any other questions? You understood, right, what Professor was asking? So, I think the quantizer zoom parameter will help you to bring it within saturation because when it goes to saturation, there will be large error. And so by adding that zoom parameter, you are scaling it basically. And when you're pushing it, it's got software scaling, right? Remember, the hardware has a problem. You're scaling it, and we do that in neural networks. And basically what it does is it puts you within that saturation range, then you do that calculation, and it comes out, you multiply it by the scaling factor, and that takes care of it. Yeah. No, selection, you select. Yeah, those are you select. Okay, but what that equation 4.17 says is, if you have errors both in E due to quantization and in U, those error terms show up. And they get multiplied with all these B and A matrices. So that's how the error becomes significant a lot of times. And it becomes significant, it can also cause instability. That's the traditional quantizer. So in a traditional quantizer, the more the number of bits, the error would be smaller, but there will be always there, it won't be zero. But with dynamic quantizer, you can make it zero. That's the beauty of the dynamic quantizer that Liberzon did. So what we did was we took it and then we showed that it does affect your Q, that is the quantized value in this case. So if I use the dynamic quantizer, then my control input, the Kalman gain will be with respect to the original value. If I don't use it, I get some error, and that is the cause of the problem. You understand that? So this is the first step. There is no system dynamics. There is no, there's still a known dynamics here. So you start with that case. Why or how this quantization affects your control input. You understood that, right? So the left-hand side is the optimal control input. The right-hand side is the equation. This first term is same as the traditional term and here we are known. The second term is probably added to accommodate the error in the quantization. Okay? Any questions on that? So this equation shows how quantization error affects the control input. Okay, any questions? All right. So what it shows is, one is the Kalman gain doesn't change, whereas the control input uses the quantized value. Look at that, xkq. So normally, so far we are using xk. But the q stands for the quantized value because you have the quantizer. Understood that? So that's the difference. So we'll skip all that. So now what happened, remember this is a linear system, we did the same steps that I showed you. So pretty much you define the new function, which is the cost to go with j of k plus 1. You can express that I already covered in the morning. So j of k plus 1 is a times x of k plus b times q of k transpose. And you get a different q matrix. And then you do the same adaptive control. And then the uqk is basically uses xkq. This is guarded xkq. And for finite horizon, dk will be time varying. Here we don't need the dynamics. So, but the only difference is the temporal difference error. Now a function of the quantized value. Don't forget that. Because you are taking the quantized value of the control input, you are taking the quantized value of the state. Because you have two quantizers. One from the sensor to the controller and the other one from the controller to the actuator. Don't forget that. So you are rewriting the same Bellman equation, but except that all these states now have quantized. You see what I'm trying to say? The approach is identical. Remember that as like a quick function. Now look at that. The only difference is the update. We can't use the same update law that I used in the adaptive control without quantization. There is a huge difference. Look at the equation there. Now, how did we come up with that? From stability. It's not something that computer science guys gave me. They don't know how to derive that. Yeah. From Lyapunov stability. You see? So Lyapunov stability. Wow, it's too loud now. Probably you don't need this mic, I keep saying that. This is one thing always my wife complained for last 27 years. I don't need a mic. She says that you need to slow down and calm down. So we have made sure that the walls are solid. Anyway, okay. So the thing is, you see all these different terms there? You need them. Otherwise, you can't prove stability. Okay? So you see that there is this EBQ. EBQ is the Bellman error. E and K is the terminal constraint error. And these terms are added to accommodate the saturation and stuff. And the basis function essentially is the time varying n minus k. I already explained to you, it has to be n minus k. N is the final time, k is the current time. So basically, this is a finite number of time instance, so you can use approximation if it's in your own network. Otherwise, it's a problem. A lot of people, control people say, how can you use time over a compact set? Okay? So this process is the same, and you see that how complex is that, and alpha theta here are the learning rate parameters. Okay? Are the learning rate parameters. And you see those zetas here? Zetas essentially are basically the history values. Remember that? So using the history, like in Bellman error, I skipped here all that stuff. Okay? So your update law, theta hat, which is same as g hat in the previous paper. So here we are writing as theta hat. So you see that the g hat is theta hat times v of k times z bar. So the theta hat is basically same as that g hat, and you have a completely different update law in order to show the stability, okay? And here is the flow chart. Now, the only difference is, if you look at the flow chart, you initialize the value function, the initial controller, which is the admissible controller. Here is the system dynamics, state quantizer. So here I'm using dynamic quantizer, okay? And that quantizer gives me values. Then I'm constructing the Bellman error and the terminal constraint error. Once you construct it, then I'm updating the G hat, okay, which is basically same as the H matrix, okay. Once I construct the H matrix, I unpack it, then I compute the control input here. I'm computing the control input. Then once I get the control input, I use the control input quantizer, which is another quantizer, and then I get the control input value, which goes to the actuator. Any questions here? Any questions? So the flow chart should tell you. Now, in the past few classes, we don't have the quantizer blocks. That's the difference. You see? And we ignored completely the quantization. Okay? All right. So then the question would come in is, really do we care? We have hardware which is 64 bits and so forth. Okay? So here are the proofs. I'll skip that. So let's go back to the batch reactor, because we are so fond of batch reactors. So you have the A matrix here, and this is the B matrix. This is discrete time, after discretization. Okay? So here we are not looking at the network aspects. The network is assumed lossless. Okay? So you see that if you look at the poles of these equations, I put the poles. One pole is at 1.22, the other pole is 1.0064, the third pole is 0.6, the fourth is 0.42. Now, is this stable or unstable system? Because a couple of poles are outside the unit disk. It's an unstable system. So inherently, batch reactor is unstable, just like the inverted pendulum. You understand that, right? So remember, I told you the optimal control, when you are designing an optimal control, that means it also stabilizes it. Goes without saying. In addition, it also optimizes it. That's the benefit over the traditional stabilizing controller, pole placement. Got it? Okay. So now I selected, in this case, Q matrix, weighting matrix, or Sn is equal to identity. And you see that the quantized value, the augmented state, has the quantized state value and the quantized control input. Okay. I'm only using one value. I don't take the history here. I'm not doing the history. Now, this is the initial state is considered as a deterministic, and K naught, the initial admissible control value, is given by that. The sampling interval is chosen as 0.1 seconds. Now, moreover, to obtain the ergodic behavior. Remember that? Monte Carlo simulation runs with 1,000 iterations were utilized. So 1,000 times I ran the simulations and we get average. So you see that because this is treated as the stochastic system. So don't forget that. For deterministic system, you don't have to deal with it. Only for stochastic system, we have to do the Monte Carlo. You typically vary the initial conditions. People also do that for deterministic because I don't know about some of you who are students here. My student gets one initial value, he shows nice result and says, I'm done. So I tell the student, you vary those initial values, initial selections, and tell me when it doesn't work. And he always comes back and says it works, but then I say, okay, pick a value which is outside the initial set and it doesn't work. So you have to pick a lot of different values and find where it doesn't work, where it works, and then you have to do it. Now, why is that? Because if you look at adaptive control, I don't know whether you have noticed this. The adaptive controller for a linear system is non-linear. How many of you know that? I know some of you took adaptive control. The adaptive control for a linear system is non-linear. So that's the learning part. Remember that. Okay? Now, do I know when I was a student? No. So, the adaptive controller for a linear system is non-linear. Why is it non-linear, guys? For a linear system. So, or the closed loop system of a linear adaptive system, adaptive control system, is non-linear. Okay, why? Why? How many of you said you have taken a course on adaptive control? No one said. I know. So if you have taken the course, did you guys do linear adaptive control or you had some non-linear as well? Mainly linear. That's what I was asking. So remember, you have a linear adaptive control, linear system, then you design an adaptive law, right? But then you compute the closed loop dynamics, error dynamics, which has it comes with a theta tilde, which is basically the error in the parameter estimation error. So why is it non-linear? Why is it non-linear? See, that's the learning part. Because, you remember you're using that update law? That update law is non-linear because it multiplies. You see here, it multiplies two state values or temporal difference error and the basis. So therefore, because it has the product or a square term in some cases, so the adaptation law is non-linear. And the closed loop dynamics become non-linear. Therefore, even though the original system is linear, the closed loop system becomes non-linear. That's why we use Lyapunov. How many of you knew this, guys? Let's be honest. Those who took the adaptive control, do you know that? Okay, this is the difference. I teach a class. Yeah. My own instructors never told me this. I had so many good instructors. No, very good instructors I have. But no, this is important because if somebody asks you in one of the interviews, yeah, I ask people, the closed loop adaptation, is it linear or non-linear? They can answer. So think about it, okay? So that's something you learned today. All right, so optimal control design flowchart. So here is the simulation stuff we have taken a discrete system. So basically for quantized design, beta is 0.9, gamma is 0.9, alpha is 0.01. We have done that. Now look at the results. So the system response and control input, right? So they are converging. They pretty much converge. There are 4 states, and when 4 states converge, the control input converges, right? There's no fun. So somebody is still wondering, why do I need the dynamic quantizer, right? Okay. So now I have plotted, there are 2 cases in this figure. Quantization error for dynamic quantizer with R equal to 4. So there are bits, 4 bits, and quantization error from a traditional static quantizer with R equal to 4. Now look at the difference in plots. So in one case, dynamic quantizer, you have a little error, but then it converges to 0, right? Look at the static quantizer. What happens after 10 seconds here? Huh? It diverges. You just select it, okay, and basically stability. You know, you pick those values so that it's within the stable range. No, we use, that's what we do, because we don't know exactly the region of stability. We still use the trial and error. Yeah. And in this case, I'm positive the student found the right result, which shows nice results. I already told you that. That's what they do, remember? So I'm positive he wants to show this, so I asked him, okay, do this, I want to see. And then I'm positive he showed me this, but he basically picked those values. Okay? So you can see that it does how it can become unstable, right? Now in this case, errors from traditional dynamic quantizers. So what I did, I want to vary the number of bits. So I want to see what will happen. So remember I told you, as I increase the number of bits, I want to see the errors in a traditional quantizer also would come down, right? And that's what happens. But there's a difference. You see, this is the result A, is the quantization error from traditional static quantizer with R equal to 8. So when R equal to 4, it blows up. When R equal to 8, you have initial errors, but it converges. Now look at the other one, the dynamic quantizer. It's perfect. You see? So there is as you increase the number of bits, quantization bits, essentially you see that the errors are much better than even our own quantizer with 4 bits. And that's what I was trying to tell you. As you increase the number of bits, the quantization error would come down, and we know that the error is typically bounded. But because of saturation, that bound can be large. You see? That bound can be large. All right? Okay. So now we look at the optimality. Remember I showed you the Bellman error. So here you see the Bellman error is driven to 0. That shows that it is optimal. And also the terminal constraint error goes to 0. So this clearly shows that we had the Q-learning coupled with the quantization. We are able to study the quantization at the same time. We are able to study that we are getting an optimal control design. Now the last plot is the difference between the known dynamics case and unknown dynamics, Q-learning. Okay, remember that. So what I did, I assumed the dynamics are precisely known without Q-learning, and then I plotted the cost. And then I did with the Q-learning that I showed you. And I'm comparing the difference. So you see that initially there's a difference because it starts with some initial value. But you see how quickly that it goes to 0. So you see how quickly it goes to 0 here. Initially there's a large value based on the initial value. But then it converges over time, and within about a second, the errors go to 0. So that difference goes to 0. That means that the system, Q-learning, learns the dynamics and generates the optimal policy pretty fast. Now, that also depends on the selection of alpha, theta, and all. So I'm positive the student probably try to, make it better. You see what I'm saying? So if you change the values of alpha, theta, you may get a long error for a longer time. But in general, it converges fast. Any questions here? So we studied what is quantization, what is static quantization, how it affects the control input and the state, right? We need 2 quantizers, one for the state to controller, other one for the controller to the actuator. And we saw how it changes the mathematics. in the control input. That's very critical. See, that's why papers get published. You have to have a mathematics to show why it affects and why is it important. Then, basically, I went back and I used unknown dynamics case because some people have done known dynamics, we are doing the unknown dynamics. We use the Q-learning. And then even with Q-learning, we are able to demonstrate if I use a traditional quantizer, things can go unstable. You see? With the number of bits. So as you increase the number of bits, 1 second, we have shown that even the quantizer, traditional quantizer becomes, and so we know that happens, but we want to reaffirm. And that's what we have shown. Whereas with the dynamic quantizer, we don't have the problem. We don't have the saturation problem. Okay? Yeah, go ahead. The number of bits, as you increase that, you can make it 0. Because you are, you saw the saturation range. The M is the saturation range. When you increase the number of bits, you are shifting that M. You see? That's what it is. Any other questions? So it has to be that simple at the end. All right. So no questions? Okay, so we'll go a little bit. Okay. Okay, here is another example. So this is a different system, A and B. This is a more simplified system, and you see that the parameter selections. And here is the basis function. So here it converges nicely. Convergence is guaranteed. In this case, there are only 2 states. And here, advantage of the dynamic quantizer. Now, why did we do that? I wanted to see if I change the system, okay, do I see the same results that I saw in the batch reactor? This is the other thing my students do. They always start with a simplified system. I keep telling them you have to pick a realistic system. Because they think that you have to write a code. In the batch reactor, the state vector is 4 by 1. In this example, this is a toy example. There is a 2 by 1, so they quickly do that, okay? So this is their first example. The other one is, I have to tell them. Now look at that. So this is the case 1, R equal to 4. Fewer number of bits leads to instability of the system with the traditional quantizer. So we saw the same problem. While stability is ensured by the proposed quantizer, you see an error initially, but it converges. Now you increase the bits, R equal to 8. Okay? So you see the traditional quantizer, the error is bounded. But there is an error. There is an error. Whereas with the dynamic quantizer, actually the error goes to 0. So the same kind of conclusion that we did for the other system also was true. The only difference is this is in color, the other one is a little black and white. Because this was used in the papers. And this is the first thing. When we wrote the book, we basically might have added the other example. And you can see the Bellman error goes to 0. That shows that the optimality is attached. And the terminal constraint error also goes to close to 0. And therefore, the terminal constraint is also satisfied. And then you want to see the difference between the 2 costs, consistency for the optimal design, and you can see that the error also goes to 0. That shows that the case of unknown dynamics converges to the case of known dynamics over time, which shows that the Q-learning is really working. Got it? All right. Okay, so I'll start with the intro. We have 5 minutes, and then I'll start. So now we are going to go into nonlinear. So far we used a linear system. So for linear system, we are always using what learning method? Q-learning, don't forget that. So for nonlinear, we are going to use what? Neural networks, because you want to approximate those nonlinearities. And then we use actor critique or one of those neural networks. So don't forget that. So when the plan becomes nonlinear, control design will become more complicated. Got it? Moreover, optimal control design will be very difficult to solve because of a JB equation, okay? So you can see this is the paper that you guys have simulated. Okay, and so these are some of our papers. The one is the iteration-based solution, the other one is the time-based solution. So now traditional optimality is if I have a nonlinear system in discrete time, and here is the value function, here is the terminal constraint, here is the cost to go. This is a finite horizon. So, and here is the terminal constraint. The optimal control policy is given by R inverse G transpose. That means you need to know the G. Partial V star. V star is a solution for the HJB equation. Okay? And here is the Bellman equation, which is the recursive equation. Don't forget that, okay? So, two issues. Partial dynamics needed, because if you look at this, in this particular case, the Travis example, remember I gave you the code yesterday, I think Dr. Vera. So here you don't need F, but you need the G. So here, we want to relax both, I think. That's why, and then one time step ahead information here. So basically you are approximating a neural network for U and maybe one neural network for V. You got it? So we are using two neural networks. Okay? So in order to estimate the dynamics, the first step is to use identifier. Now, those people who have taken adaptive control, what is the purpose of an identifier? What is the purpose of an identifier? Huh? What is the goal of an identifier? So the goal of an identifier is to estimate the system dynamics. There is a controller called indirect adaptive controller. Indirect adaptive controller, you use an identifier, you estimate the dynamics, and you use that information in your controller to design the control. Okay? So the identifier here, I'm using a neural network identifier, and what I'm doing is I'm using one neural network to approximate both F and G, and then I'm defining an identification error, which is the measured state versus the estimated state, and then I'm using history. Here also I'm using history. Look at that. Okay? So this is what is called data-driven control. So all these Chinese guys, they write a lot of papers. So they call this as a data-driven control. So basically they take the history. In discrete time, always we used history. But we never call data-driven control. Okay? So this is all this called data-driven control, data analytics, machine learning crap. There's nothing new about to me. Okay, so all this is stuff, okay? So you see that it's a data, it says x of k minus 1, x of k minus L. So all these previous values of the state and whatever, right? So then you pick up the identifier. Here is the update law for the identifier. And we show stability. That's why we pick that. So first we use an identifier. Identifier generates f hat and g hat. Got it? Now why do you need f hat and g hat? The g hat is required here. You see that there's a g there, so you need the g hat. Otherwise, so either you use two neural networks in actor critique mode, or you use an identifier and generate f hat and g hat, and you replace wherever there's f with f hat, wherever there's a g with g hat. But then the difficulty is in the proof. It's not just replacing that g with g hat, because g hat has w hat, and when you prove it, you have to bring all kinds of problems you face. Okay, so that's mainly the difficulty. So you do that. In this case, I'm approximating the value function v. You see that I'm using one neural network. Here is the terminal stage. Then I'm generating the Bellman error. Okay, I'm going to go through quickly, but we'll go back again. I'm generating the Bellman error. Now look at the Bellman error has got the v hat and all that stuff. Then I'm computing the update law for the critique. The critique uses the Bellman error. Bellman error is measured. Now there is no quantization here. So I'm doing first without quantization. You understand that? I'm doing first without quantization. And then we'll see what happens in the quantized case. So I do the terminal constraint error and then I use the total error to tune the critique weights. Now who told you those update law? It comes out from the Lyapunov stability. Understand that? So that takes a lot of time and we are skipping all that stuff. Now the control signal is also by another neural network, second neural network. Now in the control input, we have to tune. So that was a long time we were breaking our heads. In 2000, so we were the first ones to come up with how do you tune them in real time. So this U tilde is basically the U1 value from one way, the U2 value in a different way, and then we take the difference because you measure U1 hat and you measure the U2 hat. So this is the two different ways of computing the optimal control input. That's a very smart thing. When my student, he was probably spending like 3 months breaking his head trying to come up with how do we find a measured value. And these two quantities are measured. These two quantities are measured. So U1 hat is given by the output of the network. U2 hat is computed by taking the G hat and taking the partial V hat or partial X of K plus 1. So U1 hat and U2 hat are measured, but it's computed from two different ways. And we take the error and we are using to tune the actor weights. Is there a different way? No. The entire world is following this. So unless you come up with some other way, right now this is the way. Okay? So now we are tuning the actor and here is the flow chart. There is no quantized system. So you have the initialization, you update the identifier, use the information, you update, you get the value function, you basically critique updates, you compute the control input, the actor updates, and then you check the time whether you reach the final or not. Because your actor updates, you compute the control input, you apply that, and then you increase the time to K plus 1 and you go back. Okay? So this is the nonlinear neural network control for a nonlinear affine system. Okay? Now, I hope I have an example. Here are the proofs. So now let's take a two-link robot arm. So two-link robot arm, these are the dynamics. This is f of x, this is g of x. Okay? So two-link robot arm is a classical example for nonlinear system. It's a very well behaved. And this is an affine system. So most of you know what affine is? Okay. I think I see only one person, nobody is really staring at me. How many of you have taken nonlinear control? Okay, so did you guys learn about affine and what is the other one? Huh? Non-affine? No. Yeah, non-affine is there, but I don't think you might have studied non-affine. What is the second system? These are called class of systems. One is affine, what is the other one? Okay. Put a mark and find out. Homework. Okay? So this is an affine system. Okay? So the sampling interval is 1 milliseconds. The alpha is 0.9. The value function alpha is 0.01. Here is the other one for 0.1, and here are the values and so forth. Okay? And so you try to simulate it. So all nice results, right? You see that system response, they converge to 0. Very quickly the control inputs converge, but this only converges when the identification error converges. Look at that. The identification error for that f plus gu, they converges, okay? And basically, you can see that the Bellman error, it converges, the terminal constraint error converges. This is the critique weights. See, critique weights are converging as well as the actor weights also converge. So this example shows you don't require F, you don't require G, and you're using 3 neural networks, 1 for identifier, 2 for the other, okay? So I'm going to stop here because it's 12:05, and so you can do the same thing tomorrow, output feedback, and then we get into the quantized system. All right? Any questions, guys, quickly? Any questions? So tomorrow morning I'm going to ask you some of those quiz things. So make sure you come back with some answers. Okay? So otherwise we'll forget. Any questions? Okay, I think it looks like everybody's hungry. So we'll meet at what time? 2 o'clock. I think he already sent you the MATLAB code. So my gut feeling is we're going to meet. I won't be doing anything. You guys will be doing all the stuff. Okay, that's how the tutorial is. And you're going to go and show me what you got. So you're going to run the MATLAB code, right? The code is given, right? So whatever we covered, you go back and do you have the schedule on there? What is basically in the tutorial? There should be a printed stuff, right? Yeah, so you only run that MATLAB code for that particular set of systems and you play with it. So I won't do anything, it's all your work, right? And you learn from it, okay? So everybody has a laptop? I'm positive now, right? So you guys have access to MATLAB? So did anybody try running? I know these people have done, that's why they are in the front bench. So I'm asking for those who are in the back, did anybody try the MATLAB code? Doesn't look like. That's what you guys are going to do. Did you try? Huh? Okay. Yeah, so at 2 o'clock, you guys are going to do, okay? All right, guys, we'll see you. Have a good lunch. Changing the A and B matrices, but what they were doing is they really changed also the dimensions of the vector, because unless you do that, you're really not going to go through the code and make some changes. So I think I was very happy, honestly, okay? And the other nice thing they did was they kind of broke that whole problem into multiple steps. Like you see that first is simulate with a discrete time LQR, the standard LQR, where you need to know A and B matrices. So DARE stands for Digital Algebraic Riccati Equation. Okay? So I think it's not, so you need to know what is the syntax of DARE. It's already there in the code. But I'm just saying that. So once you know the dimension of the system, you make sure you understand what that is, okay? There is a noise there, and the white noise, it says you pick it and you have the command in the MATLAB. And you can pick between 0 and 1. All right? So if you look at the first problem, it says simulate the discrete time LQR for the batch system with some random delays. Then simulate the optimal controller. Okay? And then you basically you add the random delay and packet losses. You do the suboptimal control using AZ/BZ. Okay? And then you assume AZ/BZ are known, and then you try it so that you can contrast the what happens known and unknown case. And then unknown. So I think they kind of nicely, we went through that in these things, they nicely kind of split each of those questions. So I think this is a very nice way to look at different cases, distinct cases. So the only thing that changes were the dynamics and along with that the dimension of the state vector. So other than that, everything is the same. It shouldn't be that hard for you. I think how many? You have 2 problems?
I gave
4, 5. Do at least 1 or 2. I think that is sufficient. You keep doing that. Okay? So I'm going to pass it to him. I think the credit goes to him. Thank him that, So I'm going to pass it, yeah.
Okay, good afternoon. So you can already I have shared this particular assignment sheet as well as the MATLAB code. Now I am going to help you that how you will start, and once I will explain the things, I am not going to explain everything. I am going to just help you that what are the things you need to care about, and then gradually you will find that you are able to do the things what we are asking for. So if you see the problem 1, in problem 1, dynamical system in continuous time it is given, which is a batch reactor system, and I think several time you have seen this dynamics in sir's slide. Okay. And now what we wanted to do here, you will find that this system is affected by a white noise. Okay. And ultimately we want to implement the Q-learning based adaptive optimal control to stabilize this. Here some mistake is there, it will be not the inverted pendulum, it will be the batch reactor considering unknown system dynamics. Okay. Now what we want to do that, generally if you want to solve a big problem, the advice is that don't jump into the problem directly. First you think the problem can be solved in a modular way. Small problem you solve and add complexity stepwise and try to solve. Then you will find that ultimately at the end you are going to, or you are able to solve the problem what you have targeted for. Don't think that, okay, first I have to implement the Q-learning based adaptive optimal control. Don't think like that. Okay, so we will do it stepwise and we will add the complexity stepwise, and then we will correlate with the theory, and then we will able to do it. Okay, oh, fine. So that's why the first problem what we are going to do, that simulate the discrete time LQR for the batch system without random delays, packet losses as well as the noise. Okay, nothing is there. Simply you have x dot equal to ax plus bu, and now you want to implement a discrete time LQR to stabilize it. So then how you will proceed? Can anyone give a hint about that, how we will proceed? Suppose this is a continuous time system, but now we want to simulate the discrete time LQR to stabilize this particular system. So how we will proceed? What would be the first step you are thinking about? Exactly. So then you need to fix what will be the sampling time you want to sample this particular system to make the system discrete. So do you know how we can discretize a continuous time system? You know that one. So then here in your code you will find that the whole problem is also segregated in several cases. You have to extract those cases and then one by one you have to simulate. Okay? Like I am going to the MATLAB code, then only you will be able to understand what I am trying to say. Let me open the MATLAB code. Here the MATLAB code what I have shared, this is the MATLAB code I have shared. You will find for the problem 1. You will find that one folder is there which is called problem 1, and inside the problem, let me show the folder also. There should not be any confusion. You will find that this is the assignment 1, this folder I have shared with you, and this is the problem 1 folder. Okay? In problem 1 folder several other files are there, only you concentrate on problem underscore 1, this MATLAB file, you open that. Okay? Rest of the things you will automatically will able to understand what are other supporting files are there, what is the need of that. Okay, eventually you will come to know. First you open problem 1, that file. Opened? Okay, very good. Now you see what I am trying to say is that sorry, you will find that the system you see is defined here, AC and BC. This is the system. Continuous time system, so C stands for continuous. Okay, so this is the system where the continuous batch reactor system is given, that is defined here, AC and BC. Okay. Now you see, after that it is written discrete time batch reactor for NCS augment state system model. So now you see, whatever the suggestion you are going to give me, that sir, we have to select one the sampling time and we have to discretize it. So that's why you see TS is the sampling time, and TS has been defined at the beginning of the program, and it is written, you see, TS is taken 0.02, and it is written also the sampling interval. It is already mentioned, so you will be able to understand everything. So now with that we are calculating the discrete time equivalent of that continuous time system, which is written as AS and BS. And you see here, you know that to calculate A, you know that it will be, what is the formula for to calculate the discrete time case, the system matrix? AT. Exactly, you see, same thing it has been done, e to the power AT. And also there is a formula for B. Here, actually, if you see the formula for B, one integration you have to do. And for that, one function is declared here. So it is the way it has been done, but it is not mandatory that the same thing you have to follow. If you have other idea to discretize it, you can do it. But main thing is that you have to calculate the equivalent discrete time system matrix as well as the input matrix. Do it first, okay? And once it is done, then you will find that here I am saying what you have to do. These things are for the first case, it is not required. What it is required is, I am telling you. You see here, you see in green it is written that original system without random delays and packet losses with optimal control input. Means we are not considering any kind of delays, any kind of packet loss. Only we are going to stabilize the system using discrete LQR. Okay, so that's why first here the Q and R matrix are defined.